Thank you very much, Claire. So as Claire mentioned, today is World Antibiotic Awareness Day. And so I'd like to start with a question and ask, if I can see the audience, how many people here have not ever taken a course of antibiotics? So one, nobody else, okay. So one lucky person. So that means that all of us here, bar one, have experienced the near miraculous ability of these drugs to clear infections when we're suffering from an infection, okay? And that's really remarkable. So we take these drugs for granted. And since the 1940s, following the discovery of penicillin, we now all expect that we develop an infection, a bacterial infection, we're prescribed a course of antibiotics, we take those antibiotics and the infection goes away. And apart from sporadic headlines about superbugs like MRSA in Irish hospitals, we generally expect that that's going to be the case. But we now know that actually bacteria are becoming resistant to antibiotics at an alarming rate. It's a global problem, and we're not discovering new antibiotics fast enough to address this problem. So it's a crisis already. And my interest in this problem goes back a long way. In fact, I can trace it back to my time in school in St. Macartn's College in Monaghan. And at that time, when I was doing my Leaving Cert biology, I had a teacher, Jimmy Kelly, who explained to us one day about how invisible, microscopically tiny bacterial cells, so you take one of these cells and you provide it with the right growth conditions and it can reproduce fast enough to cover an entire football pitch within about 24 hours. So that for me was just a remarkable fact. And in fact, it sounded like science fiction to me, and it ignited in me a lifelong fascination with bacteria and also football. But I won't hold Mr. Kelly responsible for the football. And it's kind of important because it holds the key to understanding antibiotic resistance. It's all in the numbers, and the ability of bacteria to reproduce fast, really, really fast. And I kind of teach this to undergraduate students in Galway and previously in UCD. So bacteria are really, they're the predominant life form on the planet. Without bacteria, our life would cease. Without us, they'd be just fine. So they're remarkable organisms. For me, all bacteria are superbugs. And when they grow and reproduce really fast into huge numbers, they can mutate really fast as well. And within a huge population of bacteria, you'll have individual cells that can become resistant, and those cells then that are resistant can cause problems if they cause infections in people. And of course then, because they can reproduce so fast, they can again reproduce fast enough to cover a metaphoric football field. But it gets worse, okay? Or better if you're a bacterium. So again, back when I was at school, I learned that bacteria were single-celled organisms that like to live alone, and they weren't sophisticated like higher organisms like plants and animals and indeed ourselves. But we actually now know that that's not true. So bacteria don't like to live alone, and in fact, what they like to do is live in communities attached or stuck onto surfaces. And we call these communities biofilms. And again, it's all in the numbers. So these communities of bacterial cells living on a surface, there's safety in the numbers for the bacterial cells. And if we look at an individual bacterium that is sensitive or killed by an antibiotic, when that bacteria sticks to a surface and colonizes that surface and grows as a biofilm, the bacteria become invulnerable. Okay, so then if you think about biofilms in the context of infections, it's a real problem. So we've got infections, for example, in patients with cystic fibrosis, lung infections. We've got infections associated with implanted medical devices, infections associated with heart valves. And the bacteria, because they're invulnerable to antibiotics and indeed our own immune responses, these infections are very, very difficult to eradicate. And the structures, the biofilm structures themselves are very sophisticated structures. The bacteria aren't just randomly sticking to the surface. They're organized into city-like structures with a primitive circulatory system that feeds the biofilm and takes nutrients away. So the bacteria then use this ability to form biofilm to stick to our bodies and indeed to implanted medical devices that can be surgically inserted into our bodies if we find ourselves in hospital. So how do we tackle this problem? Well, recent history has shown us that after the introduction of an antibiotic, it's almost invariably followed by reports of antibiotic resistance. So I believe that by challenging bacteria to become resistant to antibiotics is a challenge that they'll invariably overcome. And so what we need to think about is that bacteria are smart, we need to be smarter. And rather than just simply trying to kill the bacteria, we need to somehow modify or modulate the way that they cause disease. So stop them from causing disease rather than trying to kill them. Because if you try to kill them, they'll overcome that challenge. If you try to modulate how they cause disease, well, they're going to be less bothered by that, and hopefully they won't cause such serious infections. So in my laboratory in NUI Galway, I work on MRSA infections that I mentioned before. And I work on MRSA because it's a great bacteria if you're interested in bacteria like me. So it grows fast, it's resistant to antibiotics, it forms copious biofilms on medical devices, and also it produces an array of nasty toxins that damage our bodies. So it's got it all going on in terms of being a successful pathogen that causes problems in our hospitals. So it's really earned its moniker as a superbug, and it's a scourge in most hospitals in the developed world. But it's not just a superbug, it's also a smart bug. And so the more antibiotic that you challenge MRSA with, the more resistant it becomes. So you can throw more antibiotic at it, doesn't matter, it'll just up its resistance levels. And so while studying this phenomenon in NUI Galway, I actually got lucky, okay? And what happened was that day to day when we're growing MRSA, we grow them in Petri dishes on blood agar. Okay? And the blood is actually from horses or sheep, it's not human blood. But as the bacteria grow on the surface of the agar, on the jelly-like surface of the agar, they produce toxins. And those toxins cause red blood cells in the agar to burst. And so the red-colored agar goes clear. Okay, so you can very visibly see that when the bacteria are producing all these toxins, you get a clearing, you get that red to clear change in the color of on the Petri dishes. And what I noticed was that the MRSA that were very, very resistant to antibiotics actually stopped doing that. So the plates stayed red. So they stopped producing toxins. And over time, then I realized that that was an Achilles heel for the MRSA, and that by forcing MRSA to become more resistant, i.e. by exposing it to more and more antibiotic, it actually became less and less toxic. And so how does this happen? And again, it's all about the numbers. And when you have large numbers of MRSA together, causing an infection, or for example, growing in a biofilm, which is a concentrated population of bacteria on a surface, they communicate with each other to coordinate the production of these toxins. So yes, the bacteria even talk to each other, and it's this ability of the bacteria to talk to each other that is sacrificed when they become more resistant to antibiotics. So they make a decision. Will we become resistant? Okay, if we become resistant, they sacrifice how toxic they are. So with funding from the Health Research Board, research in my lab is now seeking to use methicillin, which is actually an old antibiotic. So it was introduced into clinical practice in the 1960s, and we want to use it in a new way. Our experiments are showing that by treating MRSA with methicillin, we can subvert what is a really cool ability of the bacteria to become more and more resistant by interfering with the way that they communicate with each other, and thereby stopping them from producing toxins, which will then have the effect of resulting in less damage on our bodies during an infection. And I believe that that can be actually introduced into clinical practice, because what the research has essentially identified is that we can take an old drug, which again is already on the shelf of the pharmacy, and we can introduce it and use it in a new way to limit the severity of MRSA infections. So in closing, I just want to say that we underestimate bacteria at our peril, and approaches that I've just described, such as I've just described, are just one way that we can tackle the problem of antibiotic resistance. Antibiotic-resistant bacteria are here to stay, and resistance to this fact is futile. Thank you.